with Kafka. This is I think a counterintuitive idea. It's a thing that we all think is just not possible, but it is possible. This is an argument originally made by this guy. It's Martin Kleppmann. Most of the interesting ideas in event streaming turn out at one point or another to have their source at least proximately in Martin. I see if you build the graph of where these ideas come from, there's a lot of edges that connect to him. So I always like to recommend that you follow him if you're interested in more of this kind of thing. But it would be worthwhile to step back real quick and remind ourselves. I think we all probably know what those letters stand for these properties of a database, but I still would like to talk through them real quickly. Atomicity, consistency, isolation, and durability. What are these, and in particular, why are they a problem in the garden variety distributed systems that we build these days? So durability, let's just talk about each one. Now, what's interesting about durability, I don't think it's particularly challenging. Well, I mean, it's hard to realize, but like anything that stores data these days probably has a decent durability story. But what's interesting is if you look at like over my lifetime, the databases that large businesses were using, computers were very expensive in the early 70s, and you had to be an airline or a giant bank or, something of that scale to even want one, to some degree. But the big computers that were running businesses like that, durability meant that the database transaction log got written to tape. And then, and I guess to be fair, that's maybe a few years before I was born. And you'd if something went down, you'd just bring that transaction log back into memory, and you'd have your state back. Well, most of us, when we came of age, most people who are working in technology, and whose memories are influenced by recent decades, when you think of durability, you think of this, right? And disks don't even look like this anymore. Most of your databases are probably stored on SSDs, but when you think of durability, you think it gets written to disk. A disk will forever be this picture in your mind. Really, as you look at the history of durability, these days, if you're a piece of data infrastructure and you don't have a replication story, it's almost like you're not really durable. If you're just storing data on one disk, what does it even mean? So durability isn't especially hard to think about, but I just like pointing out it's interesting that it's been a moving target over time, and our expectations for what constitutes durability have gotten, I think, more stringent over time. All right, let's talk about atomicity. Now, the kind of textbook thing that comes to mind when we're talking about atomicity in a database is something like this. It's a database transaction, and the really funny thing is that the textbook example is often an ATM. Here's an automated teller machine, and say we're transferring money, we're adding $100 to Tim's account, and we're taking it from Gwen's account. Well, that has to take place as a single atomic unit. Both those have to work or not work. Otherwise, we'll be creating money out of nothing, and only central banks can do that. So that's bad. Now, what's funny about that is if you talk to anybody who's worked in fintech, I never have, but I've certainly known people who have, they will like actually laugh when you suggest that every database mutation in fintech is somehow atomic. They've been building distributed systems for a long time and often sacrifice atomicity. Anyway, that's an aside. This is what we think of, what's on the screen here when we think of atomicity. There's another problem, though, that's emerging in systems that a lot of us are building that are not especially large scale. You don't have to be Amazon to want this, but you've got an application, and events impinge on that application, and you perform some computation on that event, and you want to remember what you did. So what do? Well, you write it to a relational database because you're a civilized person, and that's what you do with the results of your computation. But you also, you have a graph model, and so you write it to some graph database because you've got like product recommendations or fraud detection or something that you want to do, and you need to be able to search those, and the database isn't very good at search, so you write it to Elastic also. This is not weird, right? You have these three different ways of reading data, and you need to get the data, your results, into each one. But doing those multiple writes is kind of bad, because one of these things is going to go away. Some number of them is going to go away. And now that poor application of yours has to deal with the fact that it's done multiple writes. And what does it do, right? Does it roll back the other two writes? Does it have to squirrel away that write somewhere in a log somewhere and remember to write it back to Elastic later on? It's like, that's a lot of responsibility for the application. And that responsibility can be managed by some sort of framework or layer or something like that. But again, do you want application code doing that. Ideally, you don't. That's an infrastructure responsibility. And so this atomicity problem, I think, is more interesting in terms of the systems that we are building these days. And by the way, I'm just going to make problems for like 5 minutes, and then I'll solve them with Kafka. So everything should be very bad and getting worse. All right, isolation. Again, isolation in like relational databases is actually super complicated. The again textbook account of isolation, we speak of serializable isolation, right? Like we want multiple writers on the database. We want it to look like all of those writes happened in one thread in one particular order. We could always play them back in that order. Um, Not everybody even uses serializable isolation level. The details of how databases actually behave in terms of transaction isolation are vendor specific and complex. But I want to think again of the garden variety distributed systems that a lot of us find ourselves building, where we'll have a single update in place data store in the middle, which could be a relational database, right? And multiple nodes of our application might be trying to issue writes, do reads and issue writes on a database. Like imagine the application is trying to create a new user account. And there could be somebody coming in from the mobile interface. There could be somebody coming in through a browser, many users coming in, whatever. They're people just trying to do things. So process one will ask at some point in time if there's an account for Tim, and the answer is no. But process two could ask essentially at the same time. Those will get serialized, of course, but it'll ask if there's a Tim, and process two doesn't think there's a Tim. So the straw man version of this problem is that now both of those processes think it's okay to do that right and create that Tim account. Of course, that's bad because, like the Highlander, there can be only one. So that and nobody would actually build this. Like everybody is aware enough of this problem that you wouldn't probably stumble into this bug, but you need an architectural way around this when you've got multiple uncoordinated instances of your process talking to a single update in place data store. So we need to do something there. Now, consistency, again, just working through the letters of ACID here. Consistency, I'm going to define as when we mutate the system that there are certain invariants that the system that will be enforced. For example, we can only have one of each username. Usernames are unique, or account balances have to be greater than 0. So when we're issuing a write, I don't want you to think about the database. When you think about the system as a whole, when you issue that write, the system carries that out in such a way that it enforces the invariance. So we never leave the system in a quote unquote inconsistent state, meaning there are two Tims, or Tim has negative money. All right. Now, because this is the 20-minute version, I'm going to mostly assume that you know about Kafka. There's like a hour-long, even a 90-minute version of this talk where there's a whole Kafka intro in it, but we're not going to talk about that. Now, I want to talk about how you can use Kafka to realize these properties in a system at scale. First of all, durability is, again, trivial. Kafka has a mechanism. What Kafka is a distributed log, right? Some people think of it as a message queue where the data is ephemeral in some way, but writing to a Kafka topic writes to a log on disk, and that data persists on disk until it ages out, and that retention period is completely configurable, even to infinity. So topics can be infinite storage of data in a system, can be the system of record. Not only is each one of those partitions, is it a log on disk, but they're also replicated. Like I said before, you need a replication story if you're going to store data. And Kafka does that. It writes data to disk, and it doesn't erase the data when you read it. It erases the data when you've said that the data is too old. And if you're extremely patient and you want that to be infinity, that can be infinity. And if you want that to be replicated to 10 different servers because you have nothing but money, or you're in quarantine and you're bored and you want to make operations difficult, you can make that replication factor 10. Most people use 3, but the point is Kafka accomplishes durability. All right, atomicity. Let's talk about atomicity. Now, remember, even if you don't know anything about Kafka, you probably know that has something to do with messaging, and the core data structure in Kafka is a log. Kafka calls them topics, just like enterprise message queues call their things topics usually, but a topic is a log. So when I write to a topic, that message, which is a key value pair, gets written to the log and stays there. And they stay in order as well. So I have this ordered log of messages. There's lots more nuance to how all that works, to how replication works, to the details of ordering and partitioning and how they interact. See me after class. So for now, all you need to know is that a Kafka topic is a log. Recall this problem, this application that we had put together. We're getting events and we want to write that data to multiple places. Now that's not bad to want that. It's bad to do it. If you're doing multiple writes with the results of a computation, you should probably like carry, just if you do that a lot, like put a rubber band around your wrist or something like that, snap it every time you find yourself thinking it's a good idea to write more than once. You don't want to. It's fine for there to be multiple ways to read your data, like you see here. That is 100% normal, and I think getting more normal as time goes on. But having that application do those writes is very bad. So what we're going to do is we're going to put a Kafka topic in the way. So remember I said a Kafka topic is a log. So those events arrive at the application does its computation over them. And instead of writing to Elastic or graph database or relational database or any of those things, instead of the application having any idea what those sinks are, what those readers are of the data, all it does is produce the results to a Kafka topic. That's what it does. That operation is atomic. So gets an event, does its work, writes the result to its output topic. And those little arrows down there that go from that topic to Elastic, to the graph database, and to the relational database, those are a part of a framework called Kafka Connect. So those are basically looking for new messages in that topic and writing them out to those sinks. And that's boilerplate framework code, right? Like you don't want to find yourself writing the code that consumes from a Kafka topic and then talks to the Elastic API to write it to an Elastic index. That's it's probably been written, and like I know everybody thinks their code is awesome, but your version of that is probably not materially better than some other version of it that works. So Connect is this framework where there are these little pluggable jars floating around the ecosystem that you could drop into the Connect server and post a little blob of JSON at Connect, and it says, oh, okay, you want me to read from this topic and write to Elastic that's here. You want me to read from this topic and write to this relational database that's there. And it does that. So we keep getting those results, and Connect keeps up until something dies, right? When one of those goes down, remember, our application is still atomically producing its results to that topic, and it keeps going, and the connectors that are up stay up. Now, from an observability standpoint, like I hope somebody's phone is wiggling to tell them that Elastic is down, customers can't search. It's bad that this is happening, but from an application perspective, the application doesn't have to think about atomicity because it's bad, Elastic is down, oops, okay, we brought the cluster back up, and now Connect knows, oh, the last one I read was that fourth message in, I'll just get caught up and get search up to date. Now, again, every operational consideration that could possibly make that harder than the slides make it sound, those all are still there, right? I mean, there could be a lot of traffic. There could have been some sort of traffic spike that caused Elastic to go down. And when Elastic comes back up, it has to catch up, and that can be hard. So, it doesn't make distributed systems a good life choice. It just makes this particular transactional property, atomicity, pretty easy to realize from the standpoint of the application. All right, let's talk about isolation. Remember, this was our problem when we have multiple processes reading and writing a single update in place mutable data store. And that there's nothing, again, you are not a strange person building bizarrely large scale systems if this problem presents itself. But you also don't want multiple processes trying to mutate the same data at once. So what are we going to do? Don't act surprised. We're going to put a Kafka topic in there. So what we do now, instead of giving the responsibility to those processes of creating new accounts, I'm going to go look to see if something exists, and I'll remember what I saw, and then I'll create it. That's terrible. That's too much to ask of those processes. So now what we say is we say, look, processes, you're out there, you want to make users, let me know when you want a user. That's all you do. Okay, the process submits a request or makes a claim on a username. I want there to be a Tim. And some metadata comes along with it, right? It's important that that process ID comes along there. Process 2, same thing. I am process 2. I would like there to be a Tim. Well, that's great. And now those have been submitted. And notice the kind of asynchronous feel that starts to emerge here. From the user's perspective, I'm sitting here on my phone and I've typed in my username and wrangled with my password manager to get it to create a password on mobile, which always sucks. And I tap on create account, and I'm quite synchronous. Like my attention span is low, but it's high enough that I will continue looking at my phone until the spinny thing goes away and the box turns green or box turns red or whatever happens, right? I'm trying to create an account, but on the back end here, this is asynchronous. I tapped that button, it produced a message, and in one sense, the application is done right now with that end of the deal. So let's look at what's going on the back end, and let's look at how on my phone I can turn that box red or green, because that still needs to happen. Okay, that database may be a relational database. It may not be. That may be part of Kafka's stream processing framework, a Kafka Streams application. That could be what's called a K-table in Kafka Streams. So if you know anything about streams, or if you want to look some stuff up about that, that's a worthwhile topic for quarantine research. If you do find yourself with extra time on your hands, it's a very good thing to know about. But you know what? Just think of it as a database. So there is one process that's consuming from this one topic of usernames. If you know about Kafka, then this topic absolutely can be partitioned. It just has to be partitioned by username. And if you don't know about Kafka and you don't know what partitions are in the Kafka sense, don't worry. Just think of this now as this log of username requests that's in order. And that database over there holds the current users who are currently there. And so now this application that's reading, think of this little database and table over here. This is a stream processor, reads from that topic. And for simplicity's sake, you can imagine this being just one thread reading one log, and it gets a user out, and that's Tim. And Tim exists, so we create Tim. Now there's a Tim. Well, let's read the next request, because that's what we do. It's Tim. Well, there's already a Tim. I'm sorry. I'm just going to drop you on the floor. There is no Tim, and so it just drops it. I can't create Tim twice. So it's enforcing that invariant that we discussed earlier. Now, the processes still need to know what to do. So this stream processing program over on the right, the drum with the little list of users there, also is going to expose a REST endpoint. So those processes can ask, hey, I'm process 2. Does my Tim exist? Did you make the process 2, Tim? Likewise, process 1 will say, is there a Tim? And I do mean my Tim, my process 1 Tim. So that metadata, it's not, I don't show it on the slide here, but that metadata came along with the users. We remembered we actually created process 1's Tim, not process 2's Tim. And so process 2 will see there's a Tim, but it's not your Tim. Process 1 will see there's a Tim, and it's your Tim. So they basically do that polling while the little spinny thing is happening on the phone, and I'm synchronously waiting to get that result. This asynchronous process has happened on the back end and has enforced isolation. Because remember, what we wanted the best kind of isolation to look like is like our requests happened in a single defined order by a single thread, processed by a single thread. So they always happen in the same order. And that's exactly what we got. So we never actually let the processes write to the database. They submitted requests. We had a way of serializing those requests, and we managed that writing in one thread in that stream processor. Now, again, this is a lunchtime thing we're doing, so there are questions that I won't explore, like, what if you have 60 million users and you can't do that in one thread? It is okay. There are ways to partition them, and so that each stream of user IDs is happening, being interpreted by one thread in one node in your cluster of username stream processing machines. This all scales up horizontally, maintaining the same semantics. But it's easier to think about at the small scale when you're first getting into your head. And consistency, again, just kind of falls out from the invariance enforced by R stream processors. Like we saw the unique username constraint was enforced there. All right. That is the quick version of how to get ACID transactional semantics with Kafka. Durability, that's easy. Consistency kind of falls out of our isolation solution. Isolation and atomicity, you get those by moving writes through topics when possible. There are a number of other really neat properties that emerge when you have a bunch of services interacting by exchanging immutable events. If you look for the topic, the database inside out, if you Google that phrase, there's some great blog posts and I think a small book and probably some talks by me online that you'll find. And if you want to know more about Kafka, there is one place that you ought to go, and it is developer.confluent.io.
Excellent. Thank you, Tim. Last time we attempted our applause. It's very hard to do with everyone muted, but if everyone wants to unmute here, we can try. All right.
That was neat.
Thank you. And even if you unmute, Zoom is designed to pick one voice and play it. So like if you ever try to like sing happy birthday to somebody on Zoom, it's terrible. Anyway.
Great. Thank you, Tim. Yes, I highly recommend those videos. I feel like they've been important for my architectural thinking. Like, even if you're not using Kafka, it gives you just a much better understanding of distributed systems and how things should go together and how you should be building things out.
Cool.
Really good. And you have a podcast, right, Tim?
I do have a podcast that's also linked from developer.confluent.io. It's called, well, all right. I was so impressed with myself when I named the podcast. It's called Streaming Audio, right? Because it's about event streaming and Kafka and stuff like that. Haha. Go ahead, Google that. If you Google Confluent podcast, or just go to developer.confluent.io and set that as your browser home so that it opens up every time there's a new tab. Go ahead, Tim. You have to scroll down for the podcast.
New episode. Ooh.
Woohoo. Yes, the James Urquhart episode just came out today. That was freaking fascinating. It was so fun to talk to him. He's a very smart guy. And there was, if you scroll down a little bit, Gabe, while I can shamelessly plug things, had Kent Beck on a few weeks ago.
Nice.
And that was even better. It just, I don't know if you know Kent, but I mean, you could just talk to him about stuff and smart stuff comes out of his mouth and like you're better off.
Awesome. I saw his Explore, Expand, Extract talk at some startup in New York. That was really good. So I bet that was a great conversation. Nice. Thank you very much.
You got it.
I think we still don't have Kalechi on. Is that correct? So, okay. So we'll dive into our just general business here. And first order of business is we have IntelliJ licenses to give away. So